to the cloud. And I'm gonna also move to the, let me see. Lisa is also here. I'm gonna share. And here, and we'll go and see, what's this thing? Everything moves on my screen. I got 5 people. Christina is here, so it's Christian S. Then I gotta get rid of this, Control Shift, 4H. Local time is actually 8:52, so we're again late. Tomorrow I'm not gonna be able to be late because we have a guest lecture. I'm not sure if people can hear me, but we can verify that in a second. And that's when we start. So we are recording. There are 4 people online. There's nobody in this room. People will show up later. This is being recorded. Let me take you. Where do I want to take you? Well, I guess let's confirm that people can hear me. So, Christina, can you hear me?
Yep, we can hear you. Can you hear me is the question.
It's possible that I didn't join anyway. So test speaker. Okay. 1-1.
Yeah, can you hear me?
Yes, now I can hear you. So
Awesome.
we're connected. Before we get started, I want to clarify that this is a class that's being offered 3rd time, and a significant percentage, almost half of the people in here are high school teachers. Well, our goal remains to determine whether this approach is going to be able to make an effect at high school level in terms of introducing concepts in quantum information science and quantum computing to students that may have not heard anything relevant about the math underlying those concepts. So to that effect, I want to announce that a paper that we submitted, it's not a paper, it's a talk. So it's based on a paper that I'm going to share with everybody this week. Christian and I have submitted a talk, that was our goal, at a conference in September. But I got this in the chat. And when this is the week before the last, and we need to wrap this class up with some conclusion. One conclusion should be related to whether it is possible or not to create a faculty learning community in Indiana, but maybe also elsewhere in the US, so to expand ourselves and provide high school teachers with materials, funding opportunities, development credentials, I suppose, so that they can teach this in the classroom. And then the last concept is where they will never teach it as if the curriculum does not allow it, because people will always go for the thing that would help them as they move on to college, for example. So one thing that we need to establish is if this faculty learning community, let's say it's based in Indiana, but people from other states could join if they wanted. It is sponsored by the Center for Quantum Technologies, and I have to talk to them in the fall when the meeting is in Bloomington. And given that this talk has been accepted in September, what I would like to do is to include, as I meet with everybody, I have to meet with everybody next week, sometime during the week. And students, graduate, undergraduate, as well as the high school teachers, and ask if you would like to be associated with that talk. The talk is accepted. I will share the paper. I have some extra stuff that we want to put inside, but what would be your level of involvement? You could be a co-author, you could be just mentioned over there, or you could contribute with something between now and then. And that's the announcement. And if you want to see the conference is this one. And it's part of IEEE Quantum Week. And I'll have more information this week, so that next week, they're still waiting for posters. Ours was in this category. And I got the confirmation last night, or sometime during the night. And I'm going to share the paper, the approach, and then give you opportunity to decide whether you would like to be. We have some time when we can change the author, so we can add stuff, modify things, change the abstract, and so on. And the idea remains: how is this going to help us if we want to introduce the topics to age groups of, I don't know, 6th grader, 7th grade, 8th grader, or maybe incoming freshmen, incoming students in high school or anywhere during high school. This is the thing that I would like to establish. Definitely, combination of the things next week when we say goodbye. Because we have to decide what exactly is the form in which we could organize ourselves to continue this development over the year. And since this is what, July, in September we'll have to travel there and give the talk. And it is necessary that in the talk we have some, at least a plan for how we are going to measure that this is in fact going to help, as opposed to other techniques. And to what extent. So then you're looking at my Zoom and I'm going to go on the C219. Okay, so if anybody wants to stop me and ask questions or mention something, no problem. So everybody's invited to somehow join this effort. I'm going to go to the website. And this is classes, and we're going to go and say tomorrow, don't forget, we have a guest lecture. I'm going to email everybody tonight to remind them that there's a second guest lecture tomorrow. What the topic is, what the abstract is, and the fact that if you are attending that, you get credit for the week. And now I'm going to go, where am I going to go? I'm going to go under what's due. So if you look at what's due, we're way past Deutsche and we have discussed Grover yesterday, but we didn't finish it. So this is the requirement for the week that's behind us. You have to put together a notebook that demonstrates that Grover is working. So I did this last night and I posted it, and I'm going to share it with you. And if you click on these links, you get James' video, which is very good. This is 2 or 3 years old, which means that some of the Qiskit that he's using may be outdated. And then there's a reference here, which is essentially the way he does it, but as a picture. Yeah, I'm moving up and down. Okay, so this is a picture, which means that you cannot use it because you have to type what's in and you cannot copy it and paste. Good. As long as you understand this, we're going to do this today. I'm going to provide you with a notebook. You can actually get this done in a second. But what was important yesterday is that we did a calculation using the Mrs. formalism, and then I think we did not finish it. So I'd like to finish it today. I may still not finish it today, but I want to explain how you could do it such that at every step you confirm that your calculations are right or wrong. We didn't calculate and confirm yesterday. We just got as far as we could. And then we said, okay, I'm going to finish it. So that's what we're going to do today. But for this week, the deliverable is a notebook with super dense coding. So when I click here, this thing didn't exist yesterday. You go into the old textbook from Qiskit, which says you have to understand that super dense coding and quantum teleportation are dual phenomena. And as long as you understand that, we're going to focus on the super dense coding. There's a picture somewhere that I took when I put in Kubica. And then I have 2 links. This one here is from Macaulay. That's the second picture that I have in Kubica. And then this one here is to Peter Shor. And what is important in this set of notes from his home institution is that he starts by saying, let's talk about these two theorems. And as I'm setting up super dense coding, I want you to pay attention to this so that you can then remember that these things are at the beginning of the talk. Number 1, the amount of information extractable from 1 qubit is 1 bit. Well, that sounds reasonable, right? I have a qubit. Chances are that if I want to use it to convey some information, eventually I'm going to have to measure it. It becomes a bit. Good. Now, the second part may or may not be obvious to you. In fact, he doesn't prove anything. So if people were to look up proofs or come up with their own proofs, I would be interested to see exactly what level of I guess detail you feel, at what level of detail you feel you are convinced. If nobody finds anything, or if nobody does anything about this, I do have a pointer to a lecture by Preskill, where the basic idea behind the proof is that, for the theorem 2 that I haven't even stated it, but you're looking at it, is that it's based on a density matrix. So we didn't discuss density matrices, but they are important in the formalism that you should eventually know if you're going to go, say, to the masters in QRS. you're going to learn it there, or you're going to have to know have some idea before you get into that. There are some of the resources that I posted have chapters on those. And here's the theorem. The theorem says that an entangled pair of qubits cannot carry any information. So I'm just going to tell you that it's hard to give intuitive arguments for these theorems, but I'm going to tell you that in general, entanglement is a phenomenon that is responsible for instantaneous correlations at arbitrary distances. So that's scary, isn't it? And the second thing is, but these correlations are random. So you cannot control them. You can't possibly send a message with a speed faster than the speed of light, despite of the fact that these correlations are instantaneous. Okay, that's the basic hand-waving argument. But think about this. If one qubit carries one bit of information, and if a pair of entangled qubits cannot be used to convey information, to carry any information, then if I give you a qubit and a pair of entangled qubits with another person, so I have a qubit, and then I share an entangled pair of qubits with Elmar, who is over here. So Elmar goes far away, and we share this thing, and I have a qubit, and I want to send Elmar some information. The idea would be that because we share an entangled pair, we cannot rely on any kind of information with that pair. And as far as my other qubit, he will be able to get one bit of information from it, according to this theorem. So if you just loosely put them together, I can only send him one bit of information. Superdesk coding says you can send two bits of information, meaning you can squeeze more information than you think you can at first sight. That's the idea behind why I include this as the quantum advantage. And then we're going to go and do what we have been doing throughout
Hey,
this.
Professor, one question on that last link.
Yeah.
What is the R, EPR, or what does EPR stand for?
Can you tell me what E stands for?
Is that entangled?
No, Einstein.
Oh,
Do you know what P stands for?
no.
Podolsky. And do you know R? Now I have to tell you what R is. Rosa.
Ah.
So EPR is essentially EPR is an argument that they made back in the 1930s when they were fighting with Bohr. EPR paradox. These three guys decided under the leadership of Einstein, let's show them that quantum mechanics, which we decided we put together, is in fact incomplete. Because he kept saying, I can't believe that a good God plays dice in the universe, right? So if you can turn that statement on its head, he says that dice do play God, actually. So he was not able to understand or accept the fact that it was random. So he would say stuff like, I can't believe that the moon exists only when I look at it. And so the paradox is a very carefully crafted argument, a thought experiment like Maria does with Qiskit, where it's proposed to finish once and for all this argument with Niels Bohr. And guess who eventually determined that this argument is actually faulty in its conclusion, but sound in how it was explaining everything. In other words, what they came out was an explanation that did not produce a paradox, but just explained how quantum mechanics is. John Bell, and basically his paper in 1965. So EPR are three physicists, which 1935 decided to establish that there must be something in quantum mechanics, like hidden variable theory, that would explain everything. And just that they thought that they didn't have it then, quantum mechanics was very young at the time. It was like 20 years old, 10 of which were like, first 10 years very convoluted, and then better 10 years. And still very young, extremely young. And this paper was just trying to establish once and for all that what they thought was quantum mechanics was incomplete, and there should be a totally different approach to it. Well, they couldn't. So somewhere in here, I guess there should also be a discussion about Bell. See, Bell's theorem over here. So if I scroll down, there should be later developments. What is this? This is from New York Times. That's interesting, isn't it? Bohr's reply, Einstein's argument, later developments. There were variations of that proposal with Bell's theorem coming in mid-60s and settling it once and for all. Back in the 80s, I guess Alan Aspect came up with an experiment. He got Nobel Prize 2 years ago for that. You can see it over here. All right, so this is a shortcoming of this class on account that it doesn't deal with quantum mechanics explicitly. And as a result, these little tidbits are falling through the cracks. But what is it that we have? So there is in our proposed approach to this, this would be a simple short course in which at some point questions like this could arise. And then if I were better prepared, I could just give you more complete answers right off the bat. If I knew that these questions were coming, which I should have expected anyway. But if you go on the WhatsApp,
that was very good. Thank you.
You're very welcome. And I'm going to go and say, if I go into the playlist, the Vazirani course doesn't have any misty state formalism.
Empower your students at every stage of the writing process with Grammarly's generative AI.
Just a second. I'm going
Use
to
it.
close this. Well, actually, let it be, but
It's
follow
out
it sound. So I do want to say, where exactly can we find more information about this? Should I allow a block? Should I allow a block? I guess allow. If you scroll through this, there's EPR paradox. There is an actual video. I say dismiss. And that's where he talks about this very topic. Who called it entanglement, spooky action at a distance? Einstein, on account that he just couldn't accept the idea. Even today, this phenomenon is not completely understood. And so, just a reminder, we just put it in the video. I mean, why not, right?
But this is exactly how science is, right? You do an experiment and you have some expectation, but even if you get the negative result that you can publish because you can say, hey, we thought we should get that, but we don't get that. I think it's excellent. It's exactly.
So in my view, they actually did all the work for everybody. They just had a wrong conclusion. I mean, like they, not only that Einstein came up with quantum mechanics with what he did back in 1905, mainly, not just him, but he was driving force. In the end, he rejected that. He just couldn't accept it. He says, you guys have misunderstood. It must be something else. We should do a different approach. And then he does this with Podolsky and Rosen, comes up with an excellent argument. So at the end, he draws the wrong conclusion. But again, he does the homework for everybody, except he doesn't accept it. He thinks there's a contradiction. So, Christina, this is where we acknowledged your joke, which was a big hit over here. And then let me see if I can show you what I posted. I said, I thought I posted a link. I did not post a link. I will post a link. So let me show you what link I'm going to post. So entanglement is a crucial concept that is, I think, it's still being studied by people who know a lot and still have to understand. So if you look at Preskill's paper from 2002 or 3, I'm going to say entanglement frontier. If you click here, this is from 2012 apparently. So it's just 10 years ago. I thought it was 20 years ago. The PDF is what I was going to post, but I didn't. But I'll show it to you right now. And it's a paper written for everybody, so we can understand what's happening. Okay, so I think I got carried away, seriously, because I don't know where I was when I started. We talk about EPR.
Coding.
Okay, we're super coding, that's right. An EPR pair is an entanglement. So I think this is okay. Thank you very much for bringing me back to the starting point of this. The question was, what's EPR? And then we got into that part, which is important. Then we said, Vazirani has videos about it. There's a paper here by Preskill, and we can read about it. Why is this? Why am I so super excited? Well, there is something wrong with me, but at the same time, this is the first time that we are going to deal with superdense coding. We start with a class of, I don't know where this came from, but it disappeared a bit. So we start the class of protocols that is based on entanglement. And entanglement is an issue in the sense that it's unusual. We don't have entanglement in the classical sense, the way you have it in quantum mechanics, on account that you can come up with examples of what it would mean to be entangled But then they would be like Einstein wanted them, predetermined, right? If we take a picture and we rip it in half and I take half, I don't know which half I got, and you get half. The thing is that the picture and the halves are basically set now, and we can do whatever we want. When we look at them, they are just the way they were before. On the other hand, if you are having a qubit and entangled with somebody, somebody else's qubit, one of us is going to look at them first. And when that person does that, then randomly that qubit is going to get collapsed into one state, one of the two states. The qubit then, you have no idea what you're going to get. But once you get that, the other guy immediately gets what he or she should get based on the entanglement. So if it's 0, 0 plus 1, 1, you get a 0, the other one is set on 0 immediately. And then they can do whatever they want because their qubit has been set to 0. They can look at it a million times, it's still 0. If they look at it second, not first, then it's 0 because you collapsed it from the entanglement. If you get the other value, then they get the other value. You could also get 4 bell pairs, so there could be 0, 0, 0, 1, 1, 0, 1, 1.
Then this is just theoretically if they exactly look at the same time.
Yeah, the question is, what is the same time? Okay, that's
Yeah,
the
that's
same
the
time.
thing.
How do you determine the same time, particularly since they're far away?
Because by flip-flops, you have this problem.
Yeah,
too.
especially since time dilates or contracts, if you move at a certain speed, so I think, Herman, if you want to do it at the right exact same time, given that you don't have that control, I really don't know what it means, but you can,
But when you don't know what that means, then you don't know who really sets the qubits. at
if that is even
quarter.
possible, if that is even possible, correct?
Okay.
I said, between two trains, I can put a dimensionless fly that flies faster than the trains and bounces instantaneously. Those two trains will never meet, right?
Yes.
So that's just an argument that's too theoretical. What does it mean for them to happen at the same exact time? How can you be sure that that happens? I don't know.
I don't know.
Yeah, but we think we know what same time means within a minute. It's like at the same minute. Maybe, but that's not good. So I'm going to say, I'm going to tell you that I go under what's due. And I'm going to say that the last link that I didn't show you yet is from John Waters's video. Yeah, so let me just go back and share less than a minute on this because I would like you to hear him and I want him on the video. Then you can watch the video if you want and so on. So share computer sound, I'm going to make it stereo, even though it's not necessary for that. And I'm going to click here. And so please know that besides Vasilani, who I don't think he's very happy that his videos are online. I don't think so. Because all the videos originally were accessible by everybody in edX. He taught the course back in 2012 and then again in 2020. And then he canceled it, like he made them private. But then by now there are lots of people with videos copied from him because he had allowed that. And now I'm not sure that he's happy that the playlists exist. So it's the playlist that I showed you could disappear at any time. So I have copies too. And sometimes if I have to share that there's nothing online, then I take my copy of the video and I put it in Canvas to just share with the class like I did last year. But John Waters has a different approach. This is sponsored by IBM Quantum. And so they have a sequence now, maybe 12 videos, 1 hour each, in which he explains the foundations and then he tries to explain everything in Qiskit. No misty state formalism, but regular math. So if you look into the relevant part, you can do this.
Is superdense coding. Like quantum teleportation, superdense coding is a protocol. And what it accomplishes is complementary to teleportation. Whereas teleportation allows 1 qubit to be transmitted using an E-bit and 2 classical bits of communication, superdense coding allows
So he calls an E-bit an entangled qubit.
2 classical bits to be transmitted using an E-bit and 1 qubit of quantum communication.
And that's the protocol. And I'm going to close this and I'm going to say, I hope that we're back to where this discussion started with what is EPR, because he sort of mentioned it here. I hope that you think that this is interesting because if you take these 2 elements of our protocol, communication protocol, they just don't add up. A little bit later though, so he says we won't prove these theorems now. This is transcribed by one of his students. And so if you go through this and you read, at some point it says, so it's not really a paradox. There's 2 qubits contain 2 bits of information, but when discovered, it was quite surprising. This is what the student wrote, but it's not clear how this is not a paradox. I know that they contain 2 bits of information, but one of the qubits is in fact a pair of entangled qubits, and he just said that an EPR pair does not have any information. All right, so my theory was, the thing that I was saying is that an entangled pair of qubits is responsible for instantaneous correlations, but those correlations cannot be used in any way to communicate actual information with speed faster than the speed of light. So instantaneous, that's very strange. That's why they wrote the paper. But you know, I don't want it instantaneous. If I have any chance of actually breaking the speed of light, that would be memorable. And that's not possible. So teleportation will make it clear why you can't send that information with a speed faster than the speed of light, but it remains true that entanglement is responsible for instantaneous communication, but it's random. So I guess I'm going to show you, there's a very small book in Amazon that I would like to share that I have home that I couldn't find, whatever. This is by Bettina Just. And I'm going to see this one here. So if you go inside and if I have a chance to say, look, the read sample, somewhere in this sample, hopefully, they will tell us that the formulation, instant communication at a distance, is the correlation at the distance is instantaneous but random. So this is ridiculous, and now this is actual text, and I'm not sure if I can find that. There's entanglement. Quantum particles seem to influence each other with superluminal speed over arbitrarily long distances. Okay, so they seem to influence each other, but those influences are random. You cannot use them to send a message with information with speed faster than the speed of light. There is, however, in this book written that you have the influence instantaneous. And there's also a place that says instantaneous, but at least superluminal, but not on purpose. You cannot use that information. So quantum algorithm made use of this property. This is where we are finally making use of this algorithm property, and Carla is joining us now, and that's it. So I said, look at superdense coding. Now you have a bunch of things over here that you can use, and you could always ask yourself, is it possible for me to come up with a notebook like he wants on my own now after 5 weeks or 4.5 weeks of this class? And it should be possible, again, but I'm not going to force you, because the goal would be to always provide that for you, so you can still do it if you want, and then compare with mine, or just do mine and say, now, how could I have done this? Or do I understand it? Can I explain it to somebody else? So now, what did we do yesterday? I'm going to briefly show you that if I click on the 15, I have a video which I'm going to cut the sound off. And I'm going to say that our description was basically kind of like this. And hopefully I'm going to say that this is the thing that we developed. Now, this remains our topic for today, and I'm going to post slides, complete slides of this tonight. But here's what happens, because I've done some work and I want to share this with you. So what I would like to do is to be sure that this is the right circuit, that this derivation is in fact correct while I'm doing it. All right. And yesterday we did the derivation, at some point we ran out of time. Okay. So given that this is what we did yesterday, here's what I did. We did not develop this in class, but I have this notebook that I did at home. So this is the thing that I said you should be doing based on Gene's, again, I don't know where this is coming from. It's from Zoom or from where? I don't know. From here? I have no idea. So what exactly do I have? Because I'm going to take this and change it a little bit. I am going to say that I would like to go to Google Colab. So this should be very clear. Today we have defined superdense coding to some extent. You have 2 tools, a qubit, and then a pair of entangled qubits. And your goal is to find a way to submit 2 qubits, 2 bits of information over that connection. So that's going to be our goal, and probably I'm going to have this done for you on Thursday. Tomorrow we have a guest lecture. Now, to finalize the approach, and then I will post the actual slides so you can follow along like that. As I said, I put together this this notebook. So the first thing that I do is going to be install Qiskit and the package that allows me to write nicely with LaTeX. If you look at Gene's approach, he measures things. And I say, let's not measure anything. Let's just get the actual formula so I can then compare those formulas with the things that I have in that I calculate the Mr. State formalism. Why? I can actually run out of time whenever I calculate, and if I go a little bit faster and I'm not checking my calculations, I could mess it up. I've done this already once or twice in class so far, and then I have to come back next day and clean it up. So the advice that I have now would be get rid of this. Try to do the experiment that is calculate with Misty States, and in the process verify with Qiskit at every step, and that's what I want to do now. So I will import these two things after I install them. I install them because I use a free version of Colab. And once I import them, I'm going to say that I'm going to need anything from Qiskit, or I mean more things from Qiskit than I'm going to enumerate here. And then matplotlib and numpy should be also available to me. Now, what exactly do I have over here? Well, I have an oracle. As we decided yesterday, we are going to do the oracle for 00. The oracle for 00 here is done in such a way that it exists as a circuit, and I can also use it as a subroutine. So look at this oracle for 00, and then see how it is the oracle for 00, because in 3 different cases, you could actually put qubits 0, 1, 1, 0, and 1, 1, and find out that they come through unchanged. And then if you put 0, 0, it changes the phase, which means it recognizes 0, 0. It was meant to recognize 0, 0. Good. Then we are going to work on a circuit which starts with a pair of Hadamard gates. And I say, at this point, that's the way I would like to confirm that there is a certain wave function at a certain slice, at a very specific slice in our calculation. Then I'm going to say, now oracle has been defined earlier, you see it? So because the name for that circuit is oracle, I can just append it all together on lines 1 and 0 and 1, and then draw it, and I don't show you what's inside, because it's the thing that you saw already. And then I'm going to say, what is the state after the oracle? And that should be white with a phase on top, and then all the other combinations without phase. So I could go back to the video of yesterday and ask myself, is that what I got after the oracle? Because if I didn't, then I made a mistake earlier. And if I did, the calculation up to that point is fine. You could also say, oh, so I can just calculate from here through the reflection part of the circuit, if you want. Get the formula from Qiskit and then do the calculation for the last part if you want. So I'd say that, you know, it's good to do and become fluent in the Mr. State formula, which is simple, but you need practice. But you also should always consistently try to verify your calculations with the program, for example. And then you come up with another circuit, which is, as we discussed earlier, has a purpose of reflecting the amplitudes in such a way that the amplitude of the solution is the correct solution is increased, and then the other ones are suppressed. So you have 3 parts to the circuit, and it's a simple circuit because we are dealing with 4 cases for which we only need 2 qubits. And we chose to implement the one with where the queen is under the first card, all of them face down. But in this particular case, the person who comes in doesn't know, but we put the queen under the first one. So now we always feed this circuit with 0, 0, and then at the end, in one step, we get the answer as to where the queen is in one step. So that's better than classical, where if I were to have, I guess, 1 million people come in, they would have to, on average, turn face up 2.5 cards. And we consistently, our people who would be using this in a quantum sense, they would be knowing in one step where the queen is. That's because the oracle participates. It doesn't generate the answer, but participates in producing the answer at the end of the circuit. 3 parts: preparation of the state, the oracle for that particular situation that you are setting up. There are 4 cases here. We had 3 cases in Deutsche with the Grover and Money or Tiger. No Grover, Money or Tiger. And the last part is reflection. So prepare the state oracle, and then there are 4 oracles, but we're dealing with 1 here, and then the last part of the circuit. So then when you show the whole thing, it's participating with big boxes. You say, I prepare the state, and then I could also have one that says prepare state. So these are the 3 parts. I have an oracle and then a reflection, and then I wanted to make sure that what I have done is in fact going to give me the right answer. Right, so I'm putting 0, 0, which I don't have to, because if I leave them like this, they will feed 0, 0 to them. And because the oracle is for 0, 0, at the end out comes 0, 0. And that's the whole thing. It's always going to be 0, 0. But if you replace this oracle with any of the other 3 oracles, the outcome is going to be the state recognized by the oracle, even though the oracle does not generate that state. And that's the circuit, right? Now, as I'm looking at this, I say, great, is this a good deliverable for last week? Of course. And what's a good deliverable for this one? Super dense coding. So something like this I'd like to have, but I'm going to use this differently so I can use it, so I can rely on it for all the calculations. And it's going to go like this. I'm going to create a circuit. I'm going to take all of this, except I'm not going to call it oracle. What I'm going to do is I'm going to say the circuit is a circuit of 2 qubits, and I'm just going to call it A. I don't give it any name. And I'm going to build it in stages. I like this, there's no doubt about it, except because it's A, what I'm going to do is I'm going to say, what do I have at this stage? I have nothing. Good, because I would like to not produce 3 slices. I want to produce 9 slices. So then I have something to compare with when I do my calculations. I want to know when I first come up with a mistake. If I go too fast and I forget a phase or forget a bubble of one of those qubits. So the first circuit that I have is this guy. And I'm going to say, in the process of doing this, I'm going to ask it to tell me what the wave function is. Yeah, that should be 0, 0, because that's what we do every time. So I get 0, 0, except I don't have oracle, so I should be calling it A, and from here on I'm going to be home free. Well, I have too many parentheses, but I'm going to get rid of that too. So my state is calculated, but somebody has to print it. I didn't print because I deleted it like this. So this part here, the last one is printing. So, but there's the thing. It's going to print 0, 0 because that's what we put. Always, if I have 2 wires and I don't do anything, I don't prepare any special state, which although you could prepare any state you wanted, then the result is 0, 0. Good, because my next step is what's the next slice? So the next slice is going to be, you've got to be careful right now, because everything you do to this circuit, if you do it twice, then it's going to affect the circuit twice. So I'm going to say, for example, what I would like to do right now is I'm going to take A and say, please add Hadamard gates, except now I'm going to put them on both 0 and 1. So that's a kind of a notation that showed up in the past. I never discussed it explicitly. I don't have to put an H on 0 and an H on 1. I just say put H everywhere. In this case, on these entries, 0 and 1, like a list. So out comes this, and I'm going to come back with just this part saying, so if you have the circuit that you have right now, be careful so you don't modify it twice. If I were to run 9 again, I'll get another pair of Hadamard gates. And so the circuit would be messed up. So I say, this is the answer. But we recognize this. In our case with the Mrs. formalism, this will be white, black, white, 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 black. I'm sorry, white, white, black, white, white, black, and then black, black. And we wouldn't have any probabilities, but if we were to calculate them, the amplitudes would be 1/2. So then if you square that, you get 1/4. There are 4 of them, so that would be added up. So my next step would be to say, we should put 2 X gates. Good, because I think that I should do it like this. So you have the notebook, you have the way we calculate. Now we're putting together a new notebook so we can calculate again at home and verify that everything that we are producing now is in fact what we are getting with the calculations for that we'll do later tonight or whatever. Then it's important to understand that as we do super dense coding, we will find that everything is fine. Mr. State formalism without any kind of coefficients is going to work just fine. And then we're going to say, let's take a circuit, carefully chosen, that's super small, and that will be a Hadamard gate controlling another Hadamard gate. So there's a control Hadamard, and that's controlled by, that controls the Hadamard gate. So you feed the input through a Hadamard gate, and the result will be used on the control of a control Hadamard. And you're going to say, can you calculate that with a Mr. State formalism? And the answer will be no. And then we're going to have to say, what do we do? And we're going to extend the formalism, and then we'll do teleportation with it. And then we'll do other things too, but like the GHZ game and so on. Except this is an important moment. Super dense coding is still perfectly fine with the formalism that we have right now. So now I'm going to say, what am I doing next? What I'm going to do next is going to put an X on both. And now I sliced exactly as I did yesterday on the iPad, and I'll connect the iPad in a second and start calculating as well. I just have to have this notebook online. If I don't do any kind of calculations today, I just build this thing, that's still very valuable, because then you will know exactly what stages you should be able to match using the Mr. State formalism when you calculate. So I'm going to take this guy, and I'm going to say, what's the state after this? We are now after the input, after setting up the state, after preparing the state, and then into the oracle after the first pair of NOT gates. That's the output. Do you remember yesterday when I said that those X gates don't do anything? Because they flip the colors on the individual qubits, but then you can reorder them because the order doesn't matter, but the order is preferred, and the result is the same. Well, this is the proof that that part we did okay. Now I'm going to say what I have to do right now is a control Z. This is based on what we discussed yesterday. So the control Z is again part of the oracle CZ, and this thing is different in the sense that I'm going to say put the CZ with the control on 0 and then the gate on 1, but you know that makes no difference. So it just says just pick two blobs and put them on 0 and 1, and that's one gate. That's why I don't use the square brackets. So here's the new circuit right now, and I'm going to come back here with code that says what's the state right now. And you can tell that all these pairs coming in are going to be left completely unchanged by the control Z, except when it's black, it's going to acquire a phase, which you can see in the result. So the next thing is I'm going to put another pair of X's, and I've done this before. And so it would be interesting, but this takes some time until it becomes super fast or whatever, to know if we made a mistake yesterday or not, and if we didn't, to be sure, and if we did, where exactly that happened. And that's what I'm trying to maximize the probability of finding out mistakes if we make them. So then what does this do? Just put another pair of X's. Okay, and then the oracle will have been finished. This is the oracle done. And my question is, what's coming after the oracle? And you should say, you calculated that already, I think. No, I didn't. Did I? I think so. This is the state after the oracle. You see this? I went with big chunks here, but it should be white has a phase on it. Everything else is the same as before and has no phase whatsoever. That's the X gates that are at the end of the oracle. Effective. So now we are comparing the results of two different notebooks. But again, even this is useful because who knows what we may have done here or there. So I'm going to come back through this and I'm going to say, I know what to expect as I calculated in the notebook of yesterday. This is after preparation of state and the oracle. And the answer is phase on black, white, but then everything else as before. So that checks out. We know what to expect. And we also confirm that two notebooks are consistent and we didn't make any mistake. So what's the reflection part? I need to put two Hadamard gates, two Z gates, and then control Z gates, and then two Hadamard gates, and then I'm finished. But unlike what I did over here, where I proved to you that this as a block comes in and sets the answer to be what we wanted, I'm going to slice it. I'm not going to have an oracle or a reflection block. And after every single slice, I'm going to show you what the state is, so we can then start calculating. Then I'll upload the notebook in the same place for week 4. And then I will go into the iPad and checking with the notebook, I'm gonna redo the calculations until the end. And I will post in the evening the slides of the calculation. So every single slice will be one calculation and it will be on its own little picture. So I come back over here and I say, I need to put H's. This is from the last block that's doing the reflection. The H's are going to come and say they have to be on all these lines, 0 and then 1, and that's all I have. So now I'm going to say that I would like to know what the thing is after this. And if you remember here, as well as at the end, we expect where the calculations would be most involved. I showed you yesterday in Cubitzer how we handle those. Here, a lot of things will not cancel, but at the end, a lot of things will cancel. So they're involved in both cases, but a lot of things are going to be kept as a result of the stage here. So let's see that this is in fact somewhat long. How could it be that long? There will be many components, but they will all be of the following kind. White, 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 black, black, white, black, black, and they will have plus or minus. And so if they have the same coefficients, then they will cancel each other. If they don't, then they are going to add up. But remember, this is the part where something that is good is amplified, and some things, those that are not good, are going to be suppressed. So I'm going to say, this is where I will tell you what the answer is. So we're ending up with white, white, negative white, black, I'm sorry, black, white, negative white, black, and then negative black, black. So at least we know what the answer of this state is. Though the calculation, kind of like it would be sum over paths of possible universes, I suppose. And then they will collapse at the end in just 4 things, but at the end it will collapse in 1. So the next thing that I have to do right now is 2 Z's. Okay, so I got 2 Z's, I think. They basically bring us closer to the end. This 2 blue boxes are here. And I'm going to say, let me see what the thing is after that. And that is going to change, I don't know what. Actually, it's going to be the action of Z on the first qubit and the action of Z on the second qubit. So look why this guy, which is a -1/201, is going to become plus, because the 1 will come with a phase, which will cancel this phase and it will become plus. Likewise, there's a phase over here. Except here, there's a minus already, and each one will come up with a phase from the Z individual Z gates. So then there's a minus, and I have 2 more, so the result is going to be minus still. So I'm glad that this seems reasonable. I just don't want to start calculating and then in the process of exploding, lose track of what I'm doing. I maintain that it's a very simple kind of bookkeeping, but if you're not careful or if you don't have practice, you could mess it up. And the last one is going to be choose 2 more stages. The next stage is going to be a control Z, which I will implement as follows. CZ. A CZ is going to be with 0, 1, doesn't make any difference. And then once I put that in, I'm going to ask, please tell me what is happening. This may be enough for you at this point. And the question then would be, would you have been convinced by this in the first day of class? Or are you convinced now because we have done the Mr. State formalism? Then the Mr. State formalism might still, at some point, it might become, so if it's useful, I'm not sure, but if it's useful, then it brings us here, and then it becomes a casualty or something. I don't know. It's like a problem because it slows us down. So at some point we have to give up. But as we learn, slowing things down is good. You want to say something?
Yes, because you say this now as well, because of
Liability.
school, right? For having this as a teaching instrument. And what I said about it might be quite easy to write some little Python library that you could load as well, and then you take the state vector and you turn that into So you do you get
I
use the
agree.
state formalism from state vector, and I could write this add-on if this is useful for.
No, I know. I have a project that you might be interested in with somebody from Canada. I'll tell you later, it's about Qiskit for implementing parallel operations. He wrote to me last night because apparently Gerardo is his advisor or something, and he's interested in finding somebody who knows Qiskit or is an expert or something. But wait a minute, because what you're saying, you don't have to do. I'll
Yeah,
tell you why.
there's some Python code, but I would like to have, I saw the Python code.
There is some code by this guy.
Yes, I haven't studied his code, I downloaded it just, but I think it would be cool if you just can put the state vector for Qiskit into that, and I think.
Oh, yeah, that would be better, I agree.
Yeah,
But
no,
his stuff is completely ASCII, just so you know. He has no graphics, nothing. That's just what he did. Just completely ASCII, exactly as in the book. All right, and he did one case. I don't know which case. In fact, if you don't mind, I can run this now just to see how it goes.
Yeah,
I believe I should go over here and I'm gonna say,
yes, just the library, yeah.
but it runs. So I'm gonna minimize this.
But let's take this, make it quick, and
Yeah,
So
so
package that we
I agree with you.
just could, the problem is, as you said, we cannot transfer each state vector into mystic state. But we could there use as well the numbers, like you suggested, we could do exactly what you suggested, but there is an add-on for Qiskit.
So I'm gonna try to unzip this, since we are here and or the question was, why don't we have something like this? There is something like this, and let me see if I can
Yeah,
show you this immediately. I'm gonna go inside, I'm not sure what I'm gonna go inside, the DIR. I guess like this, and I'm gonna go inside, there's a directory that looks like a PY, okay? So CD Q dash, okay? And then if I go inside, I get this, so I'm gonna run it now for you, okay? So I think I should do, I'm not sure what Python I have here, so I probably have no Python. But I do have Python, which is 3.11, that's great, so I'm gonna run Python exit. I'm gonna write Python on this guy, no, on the Q. Okay, so now I have to install NumPy.
install NumPy.
That's okay, you know what I can do? I can put it inside Colab. I never did this
In
for
Colab
you.
you can run,
Why not try it since we are in this lecture?
you just will go to the notebook there, and then you can open up there and.
Exactly, open it with idle or whatever and then copy the code inside. Because you need to know that this exists. Okay, so I'm gonna come back here and I'm gonna say, let me just run it with idle. Except it's gonna complain on account that, so edit with idle. I wanna edit with idle, but I don't think idle will have access to NumPy.
No,
I don't want to solve
But
this.
when you go into the Colab, there is something like a Python.
Do you see this?
You not even have to copy it, yeah, you not even have to copy it, because you can just run it from within Colab, because there is
I
a
see.
Python ID or a Python shell.
Okay, so now I'm going to copy it though. He says you can do much better. But at least while I'm copying, you get to see that this is a significant amount of code. May not work because of who knows aspects inside the with lines that whatever. So there's a significant amount of code. It's not like 2, 20, 30, 40 lines, but he did something here, which I've run a long time ago, maybe a year ago. And I'm gonna go edit, copy, and I'd like to see if it runs for us now inside Colab, and then I want to go back to my stuff that I was doing to finish it. So what do you think? These super extra lines, does it create a problem? No. Connecting, initializing, completed, now what? So bank robbery, this is the Archimedes that he does in the second part, and I'm not sure what answers do we get here. These are all the functions. Okay, so what am I supposed to run to be sure that I am in fact evaluating what he's putting on his website? There was a function that I had to call to show me that hey, it's working. So this is how you apply sign and whatnot. This is too many lines here, so I don't have time to do this now.
Yeah.
But it would be nice to actually go through this and
Let's be.
read while I fix the lines, because I just hate that the lines exist with empty. However,
Okay.
they don't do anything, and apparently it did work, except there isn't a place to start the program. So let me see which thing I made. There may be a comment
Yeah.
somewhere says run this.
Maybe if sometimes the main part.
Is there a main? That's the thing. I don't remember what I did a year ago. Let me quickly look through this because it wasn't too hard. So function again, simple Pete, observe. Let's see,
Underscore main.
Yeah, I'm looking for something like that, because we're like halfway through. No, I don't want to search, I want to see it. Hang on, swap, C naught, that's nice. Control naught. C control swap. Pete box is here. And usage. How about we do this, okay? I believe that this is what we are supposed to do. Bank robbery, and that's it. So now I'm saying to you, if that's the usage, well, let me drum roll whatever, and I'm gonna run this. And it says, I don't know what M1 is. So now we have to establish what M1 is. What is M1?
So it's just a variable that you have entered.
But who's M1? Because now I have to search M1.
Okay. Arching and Misty State one.
Who knows?
So let's just keep something WWBDB and.
M1 is something. See, I have to create an M1 equals like this. Oh, I have to create a circuit of some sort. M1, I want an M1 somewhere. I skip those things. So I suppose, okay, if I go through this, I guess that's the circuit. I need to create a circuit kind of in Qiskit where I put these gates, and at the end I say run it with something. But M1 is observe M1, I don't know, M2. What is M1? If this was like a mandatory class and whatnot, this could be an assignment. Take this and work it out. And then we'd come back and discuss, but I'm not assigning anything like this here. So what is M1?
I will go much simpler. It was just take the vector in Qiskit and turn it into this.
Good, that remains a very good proposition. So M1 is something like this. You're going to say, I want to initialize a state. So I'm going to show you exactly. I'll take this one completely randomly. And I'm going to go at the end. Does that make any sense? It's very debatable. But at least to show you, if I create a state, and it's the state, could I then do something with it? And it's just crazy. I'm doing random stuff here, but I'm going to run. Okay, at least M1 is not going to not exist. So what's happening? Let me show you outcome. See? Whatever I've done, which is completely unclear, is processed through what I just described, and it says the mismatch clears, and you see minus WW and then BW and then BB, which is a rearrangement of this. So this is only proof that these functions work. What I've done is unclear, is I randomly picked an M1 and then I call Archimedes on that one. Well, what you need to do is to look into the book and set it up properly, and it will then I suppose show you stuff. And okay, I'm going to close this and I say at least it runs, it's not crashing and whatnot. But it's Elmar's idea is very good for somebody in principle to take Qiskit and produce like you do here, blobs that indicate what the Misty state would be, pretty unnormalized. And so what am I supposed to do now? I'm supposed to add 2 more gates. They're supposed to be Hadamard gates, but you can tell that this is in fact what you're looking at right now is what you get after 2 Hadamard gates. Yeah, you get white, 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 black, black, white, black, black. So when I put this in the 2 Hadamard gates, I'm going to get back the white, white. This is obvious. The only part that is a little bit more difficult is that when you are coming up with the derivation, as we did earlier, yesterday, then to reach that stage, you end up with a bunch of terms that you have to manipulate carefully. And there must be some benefit to that in the beginning, at least, to bring people to something like this now. So you can say, oh, I understand this now because I've done this so many times and I don't want to do the mixed state formalism anymore. So I'm going to come and say, if I add two gates, then it will be like this. And I say, here's a Hadamat gate. On 0 and 1 on 1, and then the circuit now is complete, and it's what we expected. The first slice is the preparation of state. This one here is the oracle from yesterday, and this is the reflection chunk. And I'm coming here to say at the end, the conclusion would be 0, 0, which we know already, and we believe, and that's the outcome. So what I'm going to do is I'm going to say slice by slice, Grover slice by slice. So Grover slice by slice on 0716. And I'm going to save it like so, file, download. And I'm going to put this in here. And once it's there, I'm going to come to it and take this guy, put it here. And then I'm going to go back to my C290. I don't know where it is. I put it here. And I'm saying I'm on week 5. And this is what we are doing in week 5. Yesterday, I posted this notebook, which is great. It helped me understand. Let's see. I'm going to come back over here. Okay, I have to log in. That's the problem. So my username, C212. And my password is, let me see if I remember it. And then I sign in. And if I have to respond, I can, but I don't have to. That's good. And week 5 is with the thing from yesterday. That shows you that the gene code from 2 years ago is still good, but we do it slightly differently because we don't measure anything. We just produce the actual wave functions. And then we showed you how to create chunks that are named like subroutines, and there are 3 slices. One is not called anything, but there are 2 hadamats and they're supposed to prepare the state. Then you have an oracle marked as such oracle, and then you have the reflection circuit. And today I said, and this is what you get in this particular thing. So today I said, we can then follow along the lines of what we did yesterday for the sake of doing it again to make sure that we don't make any mistakes or that whatever we're calculating matches perfectly. And then I'm going to upload this notebook, which actually took slices at every single place. So then I'm going to say, just drop this guy here. And I could just say over here, this is slice by slice. Grover. And that's my upload is going to be marked such. And when I come back over here, I'm going to say on the week 5, the last thing that I did was this one. So this is the notebook that I created right now. And what I would do right now is essentially go inside and calculate on the iPad. I don't have the time because we got to the end. I'll do it on my own, and I will post the slides later tonight saying, this is what you do if you slice it step by step. Well, then let me do exactly the same thing with the missing state formalism, and I'll tell you if yesterday I did make a mistake or not. I don't know at this point. But at every single step, I should be able to do so. You know that if you wanted, you have 2 more oracles. One is in the qubitzer, the other one we're working on right now. There are 2 more, just for practice, you could do those. Last thing that I want to do, I'm going to go into Google Colab, and I'm going to emphasize to you the moment when I guess I go to Untitled 10. Untitled 10, so get rid of this one, supplementary material. Untitled 10 is essentially this one, and I'm going to clean it up. One day next week, I'm going to run this for you once, just because today I didn't. I just said definitions are all working, and if we were to pick out an M1, if we were to run something, then something will happen and outcomes with no error or something else, whatever. So in this case, I'm going to choose a code, and I'm going to say, let's look at the circuit. Let's look at a circuit that will crash the missing state formalism. I mean, it's not that we are hurting him because he tells us from the beginning, be careful, this formalism needs to be used with matrices which are of a certain kind. So if you don't have those matrices, then it's not going to work. So I'm going to install this. So this is coming and it has to be addressed.
So this is
It's the part that
break even, right?
yeah, I'm breaking even with the math.
Yeah.
At this point, actually, the math is getting ahead of me. And I need to do something with the formalism so that it can not crash. And the thing that needs to be done is to add the coefficients in the misty state formalism. But I don't need to add them early. I've done 4 weeks and a half, a significant range of phenomena without having to worry about coefficients. That's why I think it's valuable for people who are as young as 6th grade. But then at some point, you have to upgrade it. So then I'm going to come back here and I say, if this is finished, let's draw. And then import this and let's build that circuit. And let's build that. Okay, I'm wrong because I'm doing the thing here. Sorry about this. The next thing that I want to do is copy this one. And I have 2 more minutes and I'm going to show you that circuit that will in fact be our transition. So do I need this? I guess so. Do I need NumPy? I don't think so, but actually I don't think so. And if I do need, I'm going to come back and ask for it. So I will draw it, but I'm not going to use any NumPy. I don't think I will need. So okay, it's so from our notebook from before. I'm going to say this is my circuit. My circuit is going to be really small, and I say this is why I think this circuit could come up. So somebody opens the book, understands the first part, there are 3 parts, it says, oh, this is great. He keeps telling us about control knot and Hadamard gate. So here's what I'm going to do. I'm going to put Hadamard gate on 1. Okay, and then I'm going to put a barrier. And this is my circuit right now. So far, so good. I have Hadamard, I know how that works. But now I get confused. I'm a young student and I'm so excited that here's what I'm going to do. I'm going to say, now let's make the output of this Hadamard gate go into the control of a control gate, which normally in the book shows up as control knot. But what if I think of control Hadamard? I'm just misunderstanding a little bit. And the thing is, I can say put a control Hadamard with a control on 1 and then the gate on 0. And it looks like this, right? And now the question is, doesn't this look like what he does in the book? Yeah, except it's not. And what I would like to do is to find out what the expression is. So since today I went and calculated slices and wave functions, I'm going to say, what do you think is the answer after this stage? So a misunderstanding is I put a control Hadamard instead of a control knot. And I put Hadamard on only just one side. So this I think can come from a student that says, yeah, let's try things out. And out comes this answer. And now, because all the things that we did today was slice the circuit, print the wave function, then go and calculate the misty state formalism, I challenge you all to use the misty state formalism once you say, I am solid. I just have to go slowly, but I'm solid. Okay, see if the misty state formalism works on this circuit to produce the thing that we are looking at. And the answer is clearly not. Because as you can see, the probabilities are not symmetric. And this cannot be solved unless you put in the misty state formalism the actual probability amplitude, so you can keep track of them to get the square root of 2 over 2 instead of 1 over 2 or 1 over square root of 2 or whatever, 1 over square root of 3 everywhere. So now today we've established a context in which you can go, we can all go and finish the calculations of yesterday such that we are completely clear of what we are doing and we're doing it correctly. And then we introduce superdense coding for Thursday. Tomorrow we have a guest lecture. I'm gonna again write to everybody to say, please come because it's gonna be excellent. And now we also have this little circuit that people could misunderstand based on the book and say, this should be stuff that we know very well. And if you were to put this together, it kind of looks like what's in the book, it's not. But when you calculate, you will find out that your misty state formalism fails on you. And the reason is it has to be extended. And that's how we are going to go into teleportation, with that extension, with the extended misty state formalism. And that puts us at the end of today's class. So I'm going to say, break even point. Back. Alright. Good. So I'm gonna go file, download. And I'm gonna put this too into the week. And that's basically it for today. So if anybody has any questions, I'm open. Not, I'll see you tomorrow. For the guest lecture, it's gonna be outstanding. So that I go over here and I say, where's my week 5? It's right here, and I'm logged in already. So I'm gonna say upload files. And I say choose your files. So we're looking for better. But now I have to go through this. So it's better to drag and drop. Desktop is not gonna work for me. I have to go to users. I go to this and then users, find my stuff, and then go into desktop, and then get this one. And say open. And the chat has, oh, sorry, no problem. Yeah, it's hard. It's really hard to keep track of time. You should ask Elmar, who wants us to measure two entangled qubits at the exact same time, regardless what galaxies they are in.
I usually don't have that much trouble, but for some reason I did today. This was awful.
It happens. No, it happens. Absolutely, no problem. I'm glad. Great to see you here today. So I think I uploaded it. No, I have to push commit changes. So this would be the great even moment. And commit changes.
Even horizon.
And I go on the week 5, and then these are the things. I did this yesterday. It's the Grover for 00 on 715. I did this today to slice it so we can have because we're still learning the formalism and we're trying to get really good at it. So then we need support at every step so we don't make mistakes. And then this one is where we are going to give up on not using the coefficients, and then the coefficients will be necessary. They will be necessary. I would like to know another challenge for myself or anybody. Can the matrix of this guy or this guy only be produced in March? I was not able to get the matrix of a controlled Hadamard. Just for the paper for the qubit set. So I had to calculate by hand. It would say, I don't know what you're asking about. It can do matrices for anything, but not for a controlled Hadamard. It just doesn't want to.
Even the what is it called? The
I mean exactly what I said. I'd like to get the matrix for
I
a
think
controlled
actually it
Hadamard.
doesn't work because this is exactly the point, right? You have usually this
Of course it should work.
density matrix, that's what you want. You want to have density matrix. Not
You can calculate by hand, which is what I did. So if you say, why is this not working? I have this exercise worked out here. So if you say, what's going on? That's exactly what I did right now. Now the question is it working? And I say, no, it's not working. Because if I calculate, I get 1 over square root of 3. So then you have to calculate this matrix. This is the matrix for the Hadamard gate. This is the controlled Hadamard gate. Sorry, this one here. So this matrix is okay. You take out 1 over square root of 2, but that's just a identity matrix cross product with Hadamard. This first matrix is totally acceptable in the Mr. State formalism. This matrix is not a multiple of a matrix with integer entries. And for this reason, the Mr. State formalism fails. This is something I calculated by hand because I couldn't get it from Qiskit in March. So I would be interested now to see if they have updated it and if I can get it. But yes, any gate such as control Z, control not, control Hadamard, they all should have a matrix. It's just that in March, Qiskit was not willing to calculate it for me. So thank you once again, everybody, and I'm going to stop sharing, and I'm going to thank you, everybody, and I'm going to go stop recording, and I'm going to disconnect, and I'm going to post the recording around noon. Not sure when I stop
but this is
recording.
the density matrix, right?
No, just a regular matrix, not a density matrix. Just the matrix as a unitary for the gate. Every gate has a matrix, like X is a 2 by 2, and control not is a 4 by 4. This one, the control Hadamard has to be a 4 by 4. Are you sure? I am sure.